Hello, my name is Georgia Warren, and this is my solution to bonus problem 3. In bonus problem 3, we are considering the two-dimensional case of a uniform right triangular sheet of mass m, height h, and base b, where the thickness of the sheet may be neglected. Part A requires us to determine mathematically a vector that identifies the center of mass of this sheet in terms of h and b. In order to do this, I have drawn the triangle with height h and base b, and point C denoting the center of mass. I have also drawn the medians of the triangle, as the center of mass of a uniform triangle is at the point of intersection of its medians. In order to find the vector OC from the origin to the center of mass, I have used vector addition and subtraction. In order to find OC, I must add OH and HC, like so. In order to do this, though, I must first find HC. It's important in finding HC to understand that not only does the center of mass lie at the point of the intersection of a triangle's medians, but this point also lies 2/3 of the way along each median. So in order to find HC, I want to take half of OB, subtract OH to find the length from H to this point here, and then find 2/3 of that to take me to C. I have done this here, where HC is equal to 2/3 of half OB minus OH to make HC. Doing this, I found that HC equals 1/3 of B minus 2/3 of H. Then to find OC, what I've done is taken OH, so H, and added HC, which is 1/3 B minus 2/3 of H. And what I get for OC is that the vector's magnitude is equal to H plus B divided by 3. To find the horizontal and vertical components of this magnitude, what I need to do is split it into a horizontal coordinate in terms of B and a vertical coordinate in terms of H. OC can be split into 1/3 of H plus 1/3 of B. So I know that in the horizontal direction, we will have a coordinate of 1/3 of B, and in the vertical direction, we will have a vertical coordinate of 1/3 of H. And so OC becomes 1/3 of BI plus 1/3 of HJ. Part B of problem 3 requires me to experimentally determine the center of mass of a right triangular thin sheet using cardboard and twine. So what I've done to achieve this is constructed this triangle on a piece of cardboard, found the center of mass using the medians and the point of intersection, and connected the twine at this point. If this point here is in fact representative of the cardboard's center of mass, then when the triangle is suspended using the twine, it will lie horizontally suspended in the air. Here you can see that this is in fact the case. I have a right-angled triangle with the medians drawn and the center of mass found where the string has been connected, and when it is suspended in the air, it lies horizontally. Similarly, I have then considered a triangle that is not right-angled. What I've done with this triangle is a similar thing. I have found the medians, then I have found the center of mass, connected the twine at this point, and suspended it in the air, noting that it also lies horizontally. This is how to experimentally determine the centers of mass of two triangles. So as you can see, despite these triangles having different sized angles and different lengths of their sides, the experimental method used to determine their centers of mass hold true for both triangles, regardless of the fact that the top triangle does not in fact have a right angle.